when you break your arm, the X-ray gives you a binary answer.
Yeah, broken or not.
Exactly. There's this jagged white line on the film, and the doctor just points to it. Broken or not broken. It's clean, it's visible, and frankly, that precision is comforting. But when you consult the APICS Certified Supply Chain Professional Learning System to figure out how the heartbeat of global commerce actually works, that X-ray machine kind of, well, it shatters.
It really does.
Because suddenly you're trying to mathematically predict the future of human behavior.
Which is, the absolute definition of diagnostic muddy waters. Forecasting isn't this neat, isolated laboratory experiment. It is literally the lifeblood of business.
Right.
If a company predicts customer demand perfectly, everything just flows seamlessly. The materials arrive at the factory right when they're needed, and the final product hits the shelf exactly when a customer walks down the aisle.
But when they miss...
Oh, when they miss the mark, the consequences are brutal. They either bleed cash holding on to warehouses full of unsold inventory, or, and this might be worse, they run out of stock and watch frustrated consumers jump ship to their competitors.
Wow, yeah. So today's deep dive into the APS source material is custom tailored for you, our listener. We're unpacking the exact principles, methods, and error measurements that supply chain professionals use to navigate those muddy waters. Okay, let's unpack this.
Let's do it.
So before any analyst touches a spreadsheet to run predictive algorithms, the text lays out some philosophical ground rules, right? The first one being a strict distinction forecast must be based on actual customer demand, not incoming orders.
Yeah, and that distinction is where so many companies fail.
Yeah.
Relying only on incoming orders from intermediaries like, distribution centers or wholesalers, it creates a massive blind spot.
Because they aren't the end user.
Exactly. Orders rarely reflect what the end consumer is doing today. A distribution center might order extra inventory just to hit a freight discount. Or they might hold off on ordering entirely just to burn through stock they already have.
So if a manufacturer is just watching their own order inbox, they are reacting to the financial strategies of their middlemen, not the actual market. I imagine that creates a bit of a ripple effect.
Oh, it creates a tsunami. It's known in supply chain as the bullwhip effect.
The bullwhip effect.
Yeah. Let's say a local retailer sees a tiny spike in actual customer demand for a specific brand of paper towels, just 10 extra units. To be safe, they order 20 extra from the regional distributor.
Okay, that makes sense.
Right, but then the distributor sees that order, panics slightly about regional stockouts, and orders 40 extra from the central warehouse. And by the time that signal reaches the manufacturer, a 10-unit shift in actual consumer demand has mutated into an emergency order for 80 units. The manufacturer pays overtime to run the factory all weekend, only to realize weeks later that, well, nobody actually wanted that much product.
That is the ultimate overreaction. So you really have to look past the middlemen and measure the pulse of the person at the very end of the line.
That is the only way to anchor your data. Which brings us to, honestly, the most sobering principle in the text forecasts are almost always wrong.
Almost always.
Basically always. A forecast is merely an estimate of what will happen if there are absolutely no surprises in the world.
Which never happens.
Yeah.
So that means forecasting is less about predicting a guaranteed outcome and more about engineering a tolerance. Like building a bridge, you know the wind will blow, you just don't know exactly how hard, so you design it to sway.
That is a much better way to think about it. Every single forecast must include a calculated estimate of error. Providing a single demand number to a production manager without a margin of error is basically professional negligence. You have to plan for the variance.
What else governs the math? There's a concept here in the text called risk pooling, which claims it's easier to predict the behavior of a crowd than an individual.
Yeah, the statistical reality is that forecasts are always more accurate for aggregated groups than for single items.
How so?
Well, the APCS text uses a retail example. It's significantly easier to predict the total demand for all blue jeans across a national chain than it is to predict the demand for, one specific size of a loose-fit Levi's in one specific store in Ohio.
Oh, sure.
Or in a healthcare setting, a hospital administrator can reliably predict the total number of surgeries they'll perform next month, but predicting the exact number of emergency quadruple bypasses, it's impossible.
Right, so it's like trying to guess exactly what one specific coworker will order for lunch today versus guessing what the entire office of 50 people will order over the week. The individual's a wild card, but the crowd is a predictable statistic.
What's fascinating here is how the highs and lows of individual unpredictability cancel each other out when we zoom out to the product family level.
Right.
Someone buys 2 pairs of jeans, someone else buys none, and the aggregate number stabilizes. This allows a company to plan their overall manufacturing capacity reliably, even if the exact mix of colors and sizes fluctuates at the last minute.
That makes a lot of sense.
Yeah. And the final core principle is simply about time horizons. Near-term forecasts are inherently more accurate than long-term forecasts.
Because aiming a laser pointer at a wall 2 feet away is easy, but aiming it at a wall a mile away means a millimeter tremor in your hand sends the dot off by 50 feet.
Exactly. The further out you project, the more variables enter the equation to derail the estimate. So knowing all these limitations, the actual forecasting process is a rigid, step-by-step funnel.
Okay, walk me through it.
You determine the purpose, choose your level of aggregation, like all genes, versus just leave eyes, visualize the historical data to spot obvious patterns, pick a statistical method, and run the math. But the final and arguably most important step is sales and operations planning, or S&OP.
S&OP. The outline mentions this as the final reconciliation. I imagine this isn't just a rubber stamp meeting. Does the math actually get negotiated?
Oh, it is often the most intense meeting of the month. S&OP is where the mathematical forecast collides with human corporate behavior.
Uh-oh.
Yeah. You have the sales and marketing teams who are, well, inherently optimistic. They want the forecast to be as high as possible, so the factory produces a ton of inventory, ensuring they never lose a sale due to a stock out.
Naturally.
But on the other side of the table, you have operations and finance. They want a conservative forecast to minimize warehouse costs and avoid tying up millions of dollars in unsold goods.
So S&OP is essentially a peace treaty between the optimists and the pragmatists. They have to agree on one single set of numbers to run the entire business.
That single consensus plan is the entire goal. Without S&OP, sales is promising the moon to clients, while the factory is quietly slowing down production to save money, and it results in total chaos.
Wow. Okay, so things like the Delphi method, which is this anonymous survey of experts to avoid groupthink that protects us when we are flying blind on a brand new product launch with zero historical data.
Right, qualitative forecasting.
But what happens when a company has 10 years of sales data? Does human judgment take a backseat to the algorithm? Let's get into the actual forecasting methods.
Yeah, when you have robust historical data, human intuition absolutely takes a backseat. You move into quantitative methods, specifically time series forecasting.
M-series.
Right. Time series operates on the assumption that the underlying factors that drove demand in the past will continue to drive demand in the future. You're taking historical data points and projecting them forward. The baseline technique is a simple moving average.
So if I sold 100 units in January, 120 in February, and 140 in March, my simple moving average for April is just the average of those three, like 120 units.
You've got it. But a simple moving average treats every past month equally. January's data has the exact same influence as March's data. If you are in an industry where consumer tastes shift rapidly, that's dangerous.
I could see that.
That's why forecasters use a weighted moving average. It applies a mathematical weight to the most recent periods. You might decide that last month's sales explain 50% of the future, the month before explains 30%, and the month before that only 20%.
Which prevents old, stale data from dragging down a newly accelerating trend.
Exactly. And the most sophisticated evolution of this is called exponential smoothing.
That sounds intense.
It sounds like high-level calculus, but it's really just a specialized weighted average that requires very little historical data to calculate. It relies on a smoothing constant called alpha, which is a number between 0 and 1. The formula takes the actual demand from the most recent period, multiplies it by alpha, and then takes the forecast from that same period and multiplies it by the remainder, or 1 minus alpha.
Wait, hold on. It's blending what actually happened with what we thought was going to happen? Why do we care what we thought was going to happen if we now have the actual reality?
Because that previous forecast already contained the smoothed out wisdom of all the months prior to it. It's a compounding effect.
Oh, I see.
Yeah, if a forecaster chooses a high alpha, say 0.8, the model puts 80% of the weight on what literally just happened. It's highly reactive. But if they choose a low alpha, like 0.2, the model acts stubbornly. It puts 80% of the weight on the historical forecast, effectively ignoring a weird, chaotic spike in actual demand so the factory doesn't overreact to a random anomaly.
That makes incredible sense. You can tune the aggressiveness of the algorithm with that alpha dial. But here's where it gets really interesting. If time series methods, even exponential smoothing, are just blending past data, how do they handle a sudden, unprecedented market crash?
They fail spectacularly.
Just totally fail.
Total failure. That is the fundamental weakness of all time series methods. They inherently lag behind sudden trend shifts because their entire universe is the past. They don't predict turns, they only react to them after the fact.
It's like driving by only looking in the rearview mirror. You won't know the road curved until you're already in the ditch.
Precisely. And before we introduce the method that fixes that rearview mirror problem, we have to talk about the biggest obstacle in time series data seasonality.
Right.
If you sell snow shovels, running a moving average through December, January, and February will mathematically convince the algorithm that sales will be astronomically high in July. To prevent that, you must deseasonalize the data.
Okay, but how do you strip the winter out of a snow shovel?
You establish a seasonal index. You divide a specific month's average historical sales by the average monthly sales for the entire year. If December's sales are triple the average month, December's index is 3.0. If July's sales are a third of the average, its index is 0.33. You take your raw sales data and divide it by these indexes. This visually flattens the demand curve on your graph, removing the holiday spikes and summer dips.
So you flatten the data, run your weighted moving average on the flat numbers to find the true underlying trend, and then what? Just leave it flat?
No, crucially, you re-seasonalize the final forecast. Once the sober math is done, you multiply that baseline prediction back by the index to put the seasonal hype back into the final number.
I get it.
And it's worth noting, this kind of granular math isn't just for monthly manufacturing cycles. The service sector relies on micro-forecasting. A major fast food chain doesn't forecast by the month, they forecast by the hour.
Really?
Oh, yeah. They use time series to predict exactly when the 12:15 p.m. lunch rush peaks, so they have the precise number of registers open and French fries in the fryer, minimizing both customer wait times and food waste.
So time series is brilliant for predictable rhythms, but we still have that rearview mirror problem. If we want to look through the windshield to spot the curve before we hit it, we need something else.
Which brings us to associative forecasting.
Yes. Associative forecasting, also called causal forecasting, completely abandons the timeline. Instead, it looks for mathematical relationships between two completely different variables. You use an independent variable, the predictor, to forecast your dependent variable, which is your actual product.
So we aren't looking at our own past sales anymore. We're looking outside our own building. What makes a good predictor?
The golden rule is to find a leading indicator, not a lagging indicator.
What's the difference?
Well, the unemployment rate is a lagging indicator. It only goes up after companies have already suffered financial distress and laid people off. If you wait for the unemployment rate to tell you there's a recession, you are already in the ditch.
You want a leading indicator that signals human intent before the action happens. The APICS text uses a classic industrial example predicting the future sales of roofing shingles. The most powerful predictor for roofing sales isn't past roofing sales, it's the number of new housing starts, which are the building permits issued by the city.
Because you don't need a roof until a few months after the permit is pulled. So using a lagging indicator is like looking at the skid marks on the road to figure out there was a crash, but using a leading indicator is like seeing someone texting while driving and predicting the crash before it happens.
If I connect this to the bigger picture, mastering leading indicators is how elite supply chains survive economic downturns.
How so?
If a heavy machinery manufacturer tracks a leading indicator like the Purchasing Managers Index and sees it dip, they don't wait for their own sales to drop. They instantly pivot their supply chain away from sourcing expensive components for brand new machines, and they ramp up production on cheap replacement parts.
Because they know people will be fixing old stuff instead of buying new.
Exactly. Knowing that in 3 months, their clients will be repairing old equipment.
So we have these two data points, housing starts and roofing shingles. I imagine you can't just eyeball a scatter plot graph and guess the future. There has to be a mathematical anchor, right?
But we use simple regression. The software takes years of historical data points for both permits and shingle sales, plots them, and calculates a slope and an intercept to draw a line of best fit. Once you have that mathematical line, you simply plug next month's housing permits into the equation, and it spits out your expected roofing sales.
But hold on, the software will draw a line of best fit between any two data sets you feed it, right? What if I feed it sunscreen sales and decide that predicts my roofing sales?
The algorithm will happily draw that line, which brings up a massive warning from the text. Correlation does not equal causation.
Ah, the classic trap.
Yes. Just because two variables move up and down together on a graph doesn't mean one drives the other. Sunscreen sales and ice cream sales both spike in July, but eating ice cream doesn't cause a sunburn. They're both driven by a hidden third variable, summer weather.
So how do we verify if our predictor is actually legitimate and not just a weird coincidence?
We measure the strength of the association using the coefficient of correlation, known as R, but the truly actionable metric for supply chain professionals is R squared, the coefficient of determination.
R squared.
It tells you exactly what percentage of the variance in your demand is explained by your predictor variable. If the R squared between housing starts and roofing sales is 0.62, that means housing starts explain precisely 62% of the fluctuations in your sales.
Which means a full 38% of your sales fluctuations are driven by factors entirely outside of your model, maybe major hailstorms or interest rates. It really forces you to be humble about how much of the future you actually understand.
Humility is a requirement in forecasting, because no matter if you use exponential smoothing to analyze the past or regression analysis on housing starts to predict the future, our very first principle remains undefeated: the forecast will be wrong.
Which brings us to our final section. Measures of forecast error. If we mathematically guarantee that we are going to miss the target, we need an exact measurement of how far off we are. We need to measure the damage.
First, we categorize the type of error. Are we dealing with bias or random variation?
Okay.
In forecasting math, bias means a consistent deviation in one single direction. Your model is chronically overpredicting every single month or chronically underpredicting. Bias is dangerous because it means your underlying assumptions are fundamentally flawed, or you missed a major shift in the market.
And random variation. What's that?
That is just the background noise of human existence. You miss high by 20 units in May and miss low by 18 units in June. Over time, those misses generally cancel each other out. Your model is sound to tan. You are just dealing with statistical static.
Okay, so if we're dealing with variation, what is the core metric to quantify the miss?
The foundation of error measurement is MAD, mean absolute deviation. You take all your forecast errors over a set period, strip away the negative sign, so an under forecast of -50 is just treated as an absolute 50, and you average them.
Got it.
If your MAD is 50, it means your algorithm typically misses reality by 50 units in either direction.
Okay, so if my MAD is 50, I know my crystal ball's blurry by 50 units. Does the business just eat that cost of being wrong? Or do they use that 50 to buy an insurance policy?
Oh, they definitely buy the insurance policy. MAD is directly used to calculate safety stock. The APICS text establishes that holding safety stock inventory equal to roughly 2 MAD gives a company a 95% probability of not running out of stock during a demand spike.
Wow, that's specific.
Yeah, or if the company uses standard deviation, 1.25 MAD roughly equals 1 standard deviation. It is a direct mathematical link between quantifying your past mistakes and physically ensuring your future operations.
That is incredibly practical. We track our average miss to build a physical cushion. But what happens if our average miss starts creeping up? How do we know if our random variation is slowly turning into a dangerous bias?
We install an alarm bell called a tracking signal.
Tracking signal.
Yes. It's a ratio that tracks the cumulative sum of your forecast errors divided by your MAD. Imagine your MAD is 10 units. Month 1, you miss short by 10. Month 2, short by 10. Month 3, short by 10. Month 4, short by 10. Your running sum of errors is now 40. You divide that 40 by your MAD of 10, and your tracking signal hits a positive 4.
Because errors aren't canceling each other out, they're stacking up in one direction.
Exactly. A common industry rule of thumb is that if the tracking signal breaches a limit of +4 or -4, it automatically triggers a management review. The system is screaming that your model is no longer dealing with random noise. It has developed a chronic bias and needs to be completely recalibrated.
So MAD builds the safety net, and the tracking signal watches for systematic failure. The outline also lists MSE mean squared error. Why are we squaring the error?
Well, with mean squared error, you take every individual error and mathematically square it before averaging them. So an error of 2 units becomes 4, but an error of 10 units becomes 100, and an error of 50 becomes 2,500.
Wait, so what does this actually achieve? By squaring the error, are we basically treating it like a video game where we apply a massive penalty multiplier for huge catastrophic misses?
Right.
Does it force the software to prefer a model with consistent small errors over a model that is usually perfect but occasionally makes one massive system-breaking blunder?
You've hit on the exact mechanism. MSE is hypersensitive to outliers. A single massive forecasting failure can bankrupt a supply chain by either instantly draining cash reserves for emergency air freight or causing a total factory shutdown. Using MSE forces forecasters to select models that are highly reliable and conservative, aggressively filtering out any algorithm capable of occasionally dropping the ball that severely.
There's one final metric here that seems less about the math and more about human translation, MAPE, mean absolute percentage error.
MAP takes the absolute error and divides it by the actual demand to give you a clean percentage. The entire reason MAPE exists is because supply chain teams don't work in a vacuum. They have to secure budget from the finance department.
Right.
If the forecasting analyst walks into the CFO's office and says, our error for the quarter is 4,000 units, the CFO has no idea what that means.
Right, because if you manufacture ballpoint pens, missing by 4,000 units is an unprecedented level of accuracy. But if you manufacture commercial airplanes, missing by 4,000 units means the company is literally out of business. The raw units lack context.
But if the analyst says RMAP is 18%, the CFO instantly understands the severity of the problem. A percentage is the universal language of corporate business. It allows the supply chain team to communicate the health of their models to marketing, finance, and the executive board without having to explain the raw unit volume of every single product family.
That brings this entire system full circle. Mastering forecasting isn't just about pulling the right algorithm off the shelf. It's about managing the human biases in an S&OP meeting, actively choosing whether to look in the rearview mirror with time series or out the windshield with leading indicators, and then rigorously measuring your inevitable failures so you can calculate the exact amount of physical safety stock required to keep the world running.
It is a relentless, unending loop of predicting, measuring, adjusting, and communicating.
And the reality is, you, our listener, use these exact same APS principles in your daily life.
Absolutely.
When you look at your checking account and set next month's budget based on your average spending, you are running a moving average time series. When you notice dark storm clouds gathering on the horizon and decide to leave for work 10 minutes early, you are using a leading indicator to predict traffic congestion.
We are all amateur supply chain analysts, just constantly trying to optimize our own personal capacity against a chaotic world.
But it leaves me with one final thought to mull over. We are entering an era where artificial intelligence and quantum computing can process millions of leading indicators in real time, instantly adjusting exponential smoothing alphas across infinite product lines.
Yeah, the tech is getting crazy.
Right. So will we eventually reach a point where that fundamental ground rule that forecasts are almost always wrong becomes completely obsolete? Will the X-ray machine finally work? Or is human behavior so fundamentally chaotic and emotionally driven that the math will always, inevitably, require a physical safety stock? Something to think about the next time you try to predict your own future.